Today, we will go through the second part of mass analyzer. In this lecture, you will learn the principle and components of ion cyclotron resonance, Orbitrap, and tandem mass spectrometry. You will also learn the modes of operation, fragmentation methods, and patterns in tandem mass spectrometry. Ion cyclotron resonance (ICR) is a phenomenon that occurs when charged particles such as ions are subjected to a magnetic field or oscillating electric field at the same time. The force exerted by a magnetic field of strength B on an ion of charge Q moving with velocity V is QV multiplied with B. In order to determine the force on the ion, we first take the cross product of the velocity and magnetic field vectors. The right-hand rule tells us that the cross product will point downward. Now we simply multiply the resulting vectors by the ion's charge Q. For a singly charged positive ion, Q equal to 1. As such, the force on the positive ion will be directed downward. Conversely, for a singly charged negative ion, Q equals to 1, causing the force to be directed upward. Since the force exerted by the magnetic field is always perpendicular to the ion's velocity, it is perpetually turning the ion. The result is a circular orbit, with the ion circling around and around until other force acts on it. This phenomenon of circular ion trajectory in a static, uniform magnetic fields have been coined cyclotron motion, and the frequency of rotation is termed cyclotron frequency. The cyclotron frequency of an ion is given by QB over N. As is clear from the above equation, the frequency of any ion's rotations only depends on its mass to charge ratio and the magnetic field strength. Conveniently, the ion's velocity does not have any effect. However, the radius of the ion's orbit is dependent on its velocity, where v perp is the portion of the ion's velocity that is in the plane perpendicular to the magnetic field. Some very basic observations can be made based on these relationships. First, heavy ions will orbit with lower frequencies than light ions. Second, heavy ions will orbit with larger radius than light ions, all else being equal. Third, larger magnetic fields induce higher cyclotron frequencies and smaller radius. When ions are initially formed or placed in a magnetic field, they are likely to both have relatively small cyclotron radii and are uniformly distributed around the central axis. Both of these characteristics makes image current detection difficult, if not impossible. The small cyclotron radii means that ions does not ever travel closely to surround detection plate, therefore inducing very little image current. Likewise, the random distribution of ions around the central axis means that on average, the image currents of any one ions will be offset by the image current of an ion on the opposite side of the axis. In order to improve the ability to detect ions within the analyzer, it is desirable to both increase the cyclotron radius of ions to bring them closer to detection plates and makes the ion orbits coherently with one another. Both of these objectives are realized through the use of resonant excitation via the electric fields. Imagine an ion orbiting with cyclotron motion within an electric field. Two infinite parallel plates, one above the ion's orbit and another below. Each plate has a sinusoidal waveform applied to it, with one plate 180 degrees out of phase from the other. These opposing sine waves generate an oscillating electric field that will accelerate ions towards one plate to the other, back and forth with the frequency of the applied sine wave. If the frequency of the applied electric field is close to the ion's cyclotron frequency, the ion's motion will resonate with this electric field. As a result, the ions pick up the energy from the electric field. The increased kinetic energy is observed as an increase in the ion's cyclotron radius. Ions are detected and analyzed within a single cell inside a superconducting magnet. ICR cell is located in the center of the magnetic field and traps gas phase ions in the center using electric and magnetic fields. In order to manipulate and detect ions via FT-ICR, ions are confined within a cell. The ICR cell comprises three pairs of electrodes. The first pair is used to perform image current detection, and the second pair is used to perform resonance excitation. These first two pairs of electrodes are parallel with the magnetic field. The third pair is perpendicular to the magnetic field and is simply used to trap the ions in these acids with a small DC field. Along the magnetic field lines, ions are trapped by an applied electric potential, while on a plane perpendicular to the magnetic field lines, ions are trapped by the magnetic fields. In the previous slide, resonance excitation only addressed the excitation of a single muscle charge value through the application of a single frequency sine wave on the excitation electrode. However, in reality, there will be many ions of different muscle charge ratio in an ICR cell simultaneously. As such, it is desirable to have a method for exciting all muscle charge values at the same time with uniform strength. This objective is commonly achieved through the use of stored waveform inverse Fourier transform, or SWIFT. The SWIFT process starts by determining what muscle charge range should be excited and then calculating the respective range of cyclotron frequencies for the instrument's magnetic field strength. It also must be determined what amplitude of excitation is desired across, say, a frequency range. Having determined both the range of frequency and amplitude for excitation, an inverse Fourier transform is performed to generate a waveform that has the desired property. The SWIFT approach is superior to other methodologies because it is able to provide a uniform excitation strength across a wide range of frequencies, meaning that ions across the entire muscle charge range of interest are excited to the same degree. Since the excitation strength dictates the ion cyclotron radii, which in turn dictate the strength of the image current detected, the SWIFT approach provides a response that is proportional to ion abundance across the entire muscle charge range. Other excitation approaches suffer from non-uniformity such that equivalent ion populations at different points along the muscle charge axis will give different signal strengths due to different excitation strengths and therefore the cyclotron radii. As ions undergo cyclotron motion, they induce sinusoidal image current on the detached electrodes. Ions of different mass charge values oscillate with different cyclotron frequencies as explained above. As such, an ion population containing numerous mass to charge ratio will simultaneously induce various frequencies of image current on the electrodes. The signals collected by the electrode is a sum of these various sine waves and is commonly referred to as a transient. Although the transient is collected in the time domain, it must be converted to the frequency domain in order to create a mass spectrum. This conversion to the frequency domain above is done via the Fourier transform. Since the Fourier transform process converts the transients to frequency, which is in turn inversely proportional to mass to charge ratio, the end result is a mass spectrum. The exact shape of the peaks in the frequency domain depends on the some features of the transients itself. For example, if the sine waves in time domain have fixed intensities over time, then the peaks in the frequency domain takes the shape of a sig function. However, if the sine waves decay to near zero amplitude during the transient, then the peaks in the frequency domain have the shape of a Lorentzian. Either way, there is significant broadening of the peaks at their base. In order to minimize the effects of the wide peak base from the transform process, the transform signal is often apodized. FT-ICR follows the same principle with the magnetic sector mass spectrometer. With the curved ion trajectory, the Lorentz force is equal to the centrifugal force, where the radius of the ion motion can be described by mv divided by qb. If we consider that the kinetic energy of the ion is equal to the energy given by accelerated voltage, we will arrive at this equation describing the relationship between the ion's moving radius and other field parameters. Under high magnetic fields, the radius will be small. An ion with a very high mass would have a higher inertia, causing a longer radius. In addition, if a higher voltage is applied, the ion will have a greater radius. To wrap up, FT-ICR consists of 6 main plates, 2 excitation plates, 2 trapping plates, and 2 receiver plates. Essentially, when the excited ions moving towards the receiver plates, it would induce the current. The time domain current signal can be Fourier transformed into the frequency domain, and then interpreted as a mass spectrum. This figure illustrates the high resolution of FT-ICR using peptide MRFA as an example. The upper spectrum was acquired from the experiment, and the bottom one was obtained from theoretical isotope simulation. You may notice that the mass difference between the experimental values of FT-ICR and the theoretical values are less than 0.0002 Dalton, which can distinguish the mass difference made of one electron. We talk about the resolution. So what are the factors that can impact the resolution of the FT-ICR measurements? The first factor that comes into play is the strength of magnetic field. The stronger the magnetic field, we will have a higher resolution. If we increase the magnetic field, we will have a higher mass resolving power, a higher mass accuracy, a faster data acquisition, a higher maximum ion kinetic energy, a wider detection mass range, an increased ion trapping duration and number of trapped ions, an increased quadrupolar acylation efficiency, and a decreased peak coalescence, which means decreasing the merged peaks. The second factor is the acquisition duration. The longer the acquisition duration, the higher the mass resolution you get. This figure shows that the greater magnetic field and the longer acquisition duration both can enhance the mass resolution. A brief summary of the relationship between magnetic fields and other parameters. For the same ion, the greater magnetic fields will result in a smaller radius, a higher resolution, a faster acquisition, and a higher kinetic energy, a larger highest mass, and increase the number of trapped ions. Electric field homogeneity also plays a role in determining the mass resolution. In a cell with central excitation electrodes only, all isopotential lines meet at the gap between the excitation and trapping electrodes. Therefore, ions are heavily exposed to the axial component of the excitation field. In an improved version, the axial components inside the trapping regions are reduced by applying the excitation waveforms also to the outer electrodes, positioned adjacent to the trapping rings, and by using a grid with the excitation field applied inside the ICR cell. The mass assignment error can be described by this equation, where delta B is the error of the electric field dependent calibration parameter B. The addition of grid cells reduces delta B by a factor of 4. Same effect on delta N can be achieved by increasing the frequency by a factor of 2, for instance, by exchanging the 7 Tesla magnet with a 14 Tesla one. A homogeneous electric field with reduced axial components of the excitation field allows use of higher excitation amplitude. This results in a significantly higher ion signal. This figure shows that the mass deviation at mass to charge ratio of 524 peptide MRFA measured for the excitation amplitude of 0.25 and 0.5 respectively. The use of higher excitation amplitudes will further reduce the mass deviation. In FT-ICR, phase correction is a process to remove phase distortion that occur in the recorded signal. This is necessary to obtain accurate mass spectrum from the data, as phase distortion can cause peak broadening and shifts in peak positions. The phase correction is typically performed using algorithms that analyze the phase and amplitude information in the recorded signals and then apply correction factors to the data to remove the distortion. Fourier deconvolution-based phase correction consists of a complex division of the time domain ICR signal by the spectrum of the time domain excitation waveform to yield a phase broadened band response. The critical requirement for implementing this process is that the detection event must incorporate the excitation interval, and the excitation and detection spectra must be temporally synchronized. In practice, this simultaneously uh, excitation and detection is very difficult due to the detector saturation. In summary, FT-ICR provides extremely high resolution but very expensive. FT-ICR instrument is spatially demanding and may have the potential space charge issue. Orbitrap is an ion trap-based mass analyzer developed from the Kingdom Trap. Developed in 1923 by K. H. Kingdom, the Kingdom Trap was originally created to explore the electric potential in an infinitely long electrode. 60 years after the K.H. Kingdom passed, R.D. Knight, one of the K.H. Kingdom's contemporaries, developed the Knight trap based on K.H. Kingdom's original work. The Knight trap improved upon the Kingdom trap's limitation by deriving the mass charge values from electrical potentials, even though R.D. Knight was able to create the connection between the electric potential of an electrode to mass charge ratio. The Knight trap still had its limitation. The Knight trap had issues in discriminating between similar mass charge ratios, and the focus of R.D. Knight work was on ion ejection from the Knight trap. In the year 2000, a Russian physicist, Alexander Alexeyevich Makarov, published his work on the Orbitrap that resolved the limitation of the Knight trap. During the next 5 years, the Orbitrap mass analyzer became commercially available, allowing researchers to measure mass charge ratios of large biological samples. The right diagram shows the original design of the Orbitrap invented by Dr. Makarov. The Orbitrap gained great interest for mass analysis of biological samples because of its high resolution and high mass limit. Most other mass analyzers are limited to molecules 2 kilodalton to 4 kilodalton in size. This will require having samples to have a charge greater than 50 to be able to measure that sample with a mass of 100 kilodalton. In the case of the Orbitrap, the resolution limits are from 50 kilodalton to 100 kilodalton. For biological samples weighing 100 kilodalton, we will only need the charge of 1 to detect it in the Orbitrap. This is due to the high sensitivity of the Orbitrap having one of the highest resolution limits compared to other mass analyzers. The Orbitrap mass analyzer operates by oscillating ions in a cylindrical electrode with tempered ends and detects signal for mass-to-charge ratio based on Fourier transforms. The electrode is powered by an RF frequency that makes the ion oscillate around the inner electrodes. This figure illustrates the side view and cross sections of the Orbitrap as ions circulate through the trap. When ions are initially injected, ions typically follows an imperfect oscillatory motions with frequencies out of phase with the electrodes, like panel A, where the increase in voltage on the central electrode squeeze the ions to a curved trajectory around the central electrode. As time progresses, hundreds of oscillations become incorporated into the Orbitrap and follow more in-phase circular revolutions at panel B. However, if the initial injections of ion resonate with the electrodes, a circular orbit can be obtained from the beginning, like panel C. The moving ions are trapped around the electrodes. where the electrostatic attraction is compensated by centrifugal force arising from the initial tangential velocity. The potential barriers created by n electrons confine the ions axially. One can control the frequency of oscillations by shaping the electrodes appropriately. In addition, the high charge capacity can be achieved due to the shielding effect of the central electrode, as ions cannot see the ions on the other side of the electrode, and those minimize the space charge effect. The formed iron ring would oscillate back and forth along the central electrode with a frequency of omega. This movement will be detected on the outer electrodes. The oscillating frequency can be described by the square root of k over mass to charge ratio, where k is the field curvature. Like the principle of FT-ICR, the detected time domain signal will be Fourier transformed into the frequency domain. Thus, a calculated frequency is inversely dependent on the mass to charge ratio, and accordingly we could obtain a mass spectrum. So far, we have introduced 5 major types of mass spectrometers. This table summarizes the comparative pros and cons of these mass analyzers, just for your reference. Next, let's talk about tandem mass spectrometry. Tandem mass is also denoted as mass spectrometry/mass spectrometry, incorporating at least two stages of mass to charge analysis. The mass-mass analysis can be achieved either based on Tandem-in-space or Tandem-in-time concept. Both instrumental concepts can be expanded to allow for multi-stage mass spectrometry. Tandem-in-space refers to mass-mass instrumentation where product ion spectra are recorded using spatially separated mass-to-charge ratio analyzers. Specific mass-to-charge separation is performed so that in one section of the instrument ions are selected, then dissociated in an intermediate region, and the products thereof are finally transmitted to a second analyzer for mass analysis. Tandem-in-space examples include TOF-TOF, QQQ, or QQ-TOF, etc. Tandem-in-time, on the other hand, uses a single mass-to-charge analyzer that may be operated by executing the discrete steps of ion selection, activation, and product ion analysis in the very same place, but sequentially in time. Typical examples include ion trap, FT-ICR, and Orbitrap. This diagram illustrates the differences between the tandem-in-space mass and tandem-in-time mass. The number of mass analyses is limited in the tandem-in-time mass, whilst tandem-in-time mass can theoretically achieve numerous stages of mass analysis. Let's look into the internal setup of the most commonly used mass spectrometer for quantitative analysis, triple quadrupole mass spectrometry. Literally, triple quadrupole mass spectrometry contains 3 quadrupoles, Q1, Q2, and Q3. Q1 and Q3 are standard mass filter quadrupole with a unit mass resolution, while Q2 is an RF-only quadrupole, also called collision cell, which is filled with gas and allows the mass fragmentation to occur. Q2 collision cell does not filter ions. It accepts all ions sent from Q1 and passes all ions formed by collision to Q3 to be sorted. As mentioned in our previous lecture, Quadrupole mass spectrometer can be operated in full scan or selective ion mode. In full scan mode, 99% of the ions are lost between the rods, resulting in poor full scan sensitivity. On the other hand, in SIM mode, 100% of the selected ion reaches the detector, bringing a high SIM scan sensitivity. Fragmentation is controlled by the applied energy when the ions enter the collision cell. The higher the collision energy, the more fragmentation you expect. Q2, the linear accelerator collision cell, is usually filled with high purity helium, nitrogen, or argon gas. The collision cells also drive the ion out, reducing the crosstalk among ions. In collision cell, the analyte molecule undergo collision-induced dissociation by an energetic collision with the nitrogen or argon molecule. The fueling gas also acts to cool the fragments, facilitating transport to the detector. With the different combination of full scan or SIM in Q1 and Q3 mass filter, tandem mass experiments can be classified into 4 major operating modes, including the product ion mode, the precursor ion mode, neutral low scan, and selective reaction monitoring. The scanning mode of each mass filter is denoted with the pictogram symbols from Q1 to Q3, where the solid circle stands for selective ion mode and open circle stands for full scan mode. In the following slides, we will introduce each operation mode in details. In the product ion scan, a precursor ion is selected in the Q1 and allowed to fragment in Q2. The resulting fragments are then scanned in the Q3 and detected in the detector that is positioned after the Q3. Product ion spectra can provide structural information of an analyte, and those is an important step to select the transition pairs for the SRM mode. In precursor ion scan, all the injected molecules are scanned in Q1 and fragmented in Q2, but only a specific fragment is selected in Q3. Using precursor ion mode can investigate the compounds containing the same functional group of interest, such as chemical species from the same lipid family. However, precursor ion scan cannot be done with time-based mass instruments. Neutral low scan. All the injected molecules are scanned in Q1 and fragmented in Q2. The Q3 also scanned, but at a set offset from Q1. This offset corresponds to a neutral loss that is commonly observed for the class of compounds. In a constant neutral loss scan, all precursors that undergo the loss of a specific common neutral are monitored. Like precursor ion scan, neutral loss scans cannot be done with time-based mass instruments. In selected reaction monitoring, both Q1 and Q3 are set to a selected mass, usually representing the fingerprint of the molecule. As Q1 and Q3 are all operated in SIM mode, the selective reaction monitoring can achieve the highest sensitivity and specificity compared with other operating modes. Therefore, the SRM is commonly used for quantitative analysis. Multiple reaction monitoring essentially is a multiple SRM. One can simultaneously or nearly simultaneously monitor the SRM transitions of the quantifier and qualifier of an analyte which would further enhance the analytical specificity. However, the instruments may spend less time or duty cycle in each SRM channel if we include too many SRM channels for monitoring, which may result in loss of sensitivity. According to the place where fragmentation occurs, it can be classified as in-source fragmentation or post-source fragmentation. As the ionization process applied voltage to the droplets or ions, the extra energy may elicit metastable fragmentation, naso-schema fragmentation, or in-source decay. Except the aforementioned collision-induced dissociation, the post-source fragmentation can include the post-source decay in time-of-flight mass spectrometer. If the product ions persist in their non-equilibrium states for a moderate amount of time before auto-dissociation, this process is called metastable fragmentation. Naso-schema fragmentation refers to the purposeful induction of in-source fragmentation by increasing the naso-schema potential on the electrospray-based instruments. It is not technically tandem mass spectrometry unless metastable ions are mass analyzed or selected before auto-dissociation, and the second stage of analysis is performed on the resulting fragment. An in-source decay fragmentation occurs in the ion source via stochastic radical formation. ISD appears to occur through hydrogen radical transfer from matrix ions in the ion cloud. No energy relocation to labile bounds, as in CID, occurs on the sub-nanosecond time scale. Energy can also be added to the ions, which are usually already excited, through post-source collisions with neutral atoms or molecules. The absorption of radiation or the transfer or capture of an electron by a multi-charged ion. Collision-induced dissociation (CID) involves the collision of an ion with a neutral atom or molecule in the gas phase and subsequent dissociation of the ion. Post-source decay in the time-of-flight mass spectrometer refers to the fragmentation of a molecular ion that occurs after it has been extracted from the ion source and prior to reaching the detector. This process provides additional information about the structure of the ion and can increase the sensitivity of the measurement. The PSD process occurs in a specific region of the TOF analyzer known as the post-source region. When the vaporized organic sample passes into the ionization chamber of a mass spectrometer, it is bombarded by a stream of electrons. These electrons have a high enough energy to knock an electron off an organic molecule to form a positive ion. This ion is called the molecular ion M plus or M plus with an electron. The dot in the second version represents the fact that somewhere in the ion there will be a single unpaired electron. That's one half of what was originally a pair of electrons. The other half is the electron which was removed in the ionization process. The molecular ions are energetically unstable, and some of them will break up into smaller pieces. The simplest case is that a molecular ion breaks into two parts, one of which is another positive ion, and the other is an uncharged free radical. The uncharged free radical will not produce a line on the mass spectrum. Only charged particles will be accelerated, deflected, and detected by the mass spectrometer. These uncharged particles will simply get lost in the machine. Eventually, they get removed by the vacuum pump. The ion X plus uh, will travel through the mass spectrometer just like any other positive ion and will produce a line on the stick diagram. All sorts of fragmentation of the original molecule ions are possible, and that means that you will get a whole host of lines in the mass spectrum. For example, the mass spectrum of pentane look like this, where the yellow shades highlights the fragments of pentane. In the following slides, I will introduce you the common fragmentation patterns that can be found in each molecule class. Alkane being the simplest organic compound, you expect the fragments of simple alkyl group. On the right is an example of 2-methylpentane, where you can find the losses of methyl group, ethyl group, and propyl group. For alkenes, fragmentation typically occurs at the carbon atom next to the double bond. Forming a resonance stabilized allylic carbocations, for instance, trans 2-hexane prefers to lose the ethyl group, forming the positive charge at the allylic position. This positive charge can resonance with the double bond. Following the same principle, aromatics also prefer to form the carbocation next to the aromatic ring. The carbocation will resonance with electrons on the aromatic rings. For alcohols, fragments can be easily formed upon collision. Alcohols may lose hydroxyl radical or water, where arsenium ion is the common fragments found from alcohols. In primary alcohols, we usually can observe a prominent peak at the mass charge ratio of 31, corresponding to H2COH. For the fragmentation pattern of amines, we would expect the alpha cleavage to occur, forming the iminium ion. For the fragmentation patterns of ethers, you can expect that alpha cleavage to occur and the loss of alkyl group, forming the arsenium ion or a carbocation fragment. On the right is an example of diethyl ether, where you can find these fragmentation patterns. The common fragments in aldehydes include the loss of hydrogen from the aldehyde group and the loss of aldehyde group itself. On the right is an example of hydroxyaldehyde, where you can also locate these fragments. Ketones can either lose the R or R+, forming the acylium ions. These fragmentation patterns can be observed in the mass spectrum of 2-pentanone. Lastly, for esters, you can anticipate the loss of OR+. On the right is a mass spectrum of benzyl ester, where you can find the loss of OCH3, being the most dominant cleavage observed. Alright, that's for today. See you next time.